Hi class. In this video, I'm going to walk through the solutions to numbers 23 and 24 from section 5.3, which was the collaborative activity we did in class a couple weeks ago. And I've got some videos from your classmates to help me out. Let's start off with number 23, which I'll write out right now. So we have here a system of two linear equations with two functions, two unknowns. And this is written in our operator format, which we cover in section 5.2, which is kind of a shorthand notation that enables us to manipulate these systems of equations a bit more like algebraic equations, instead of thinking about them as differential equations. And so we'll see here, what we want to show here is that these systems are degenerate. And that may be as a concept that you have seen. If you haven't heard the word, you've certainly seen the concept when you've been talking about algebraic systems in the past, where um, the equations, you've got two equations and two unknowns, but they might um, not have any solutions, or they might have infinitely many solutions. And the reason where that kind of makes sense, let's think about these if they were like uh, linear equations, like ax plus by equals c, and then dx plus ey equals f. So these are both these are each equations of a line, right? And they might have they might have a unique solution if they go like that, or they might, I'm going to draw our three possibilities here. They might have no solutions at all if they're parallel and they never intersect. So there's no point that satisfies that lies on both lines. Or they might be exactly the same line. So this is one solution, no solutions, or infinite solutions. And the same thing happens here with our differential equations. So we're going to see Elle work out the solution to this. And so let me put the video up now.
Okay, so this is number 23. These are the original equations we're given. So I multiplied the first equation by d plus 2 and the second equation by d minus 1 to get these equations. And then these will cancel out. So you're left with this equal to this. So I multiplied d plus 2 times negative 3e to the negative 2t, which gave us the derivative of that, which was 6e to the negative 2t, which will cancel out to 0. And then I multiplied d minus 1 times 3e to the t, which the derivative of that is just 3e to the t, which will cancel out, also be 0, which means that there is infinitely many solutions.
So what Elle did was just work out the algebra in this system. So starting with what we were given, she wanted to make the left-hand sides equal, which you could also have done by trying to eliminate one of the variables. So in any case, what she did is observed that because we have d minus 1 and d minus 1 here, if we multiply the whole first equation by, or operate by, so I'm going to put quotes over multiply by because it's really operating by d plus 2, and then do the bottom one by d plus, or d minus 1, then the left-hand sides will be equal. And so they will equal whatever you end up getting on the right-hand side. So she did that. She did both of those operations here and here. The left-hand sides are equal. So that means that these two have to be equal. And the right-hand sides are what you get by operating d plus 2 and d minus 1 on those exponential expressions. So now she's done that, and operating on it means taking derivatives. So d plus 2 of the exponential is, you have to take the derivative there. And so you end up with 0 for both of them. So what she's shown is that the system is equivalent, because she just did some algebraic manipulations. The system is equivalent to this equation, 0 equals 0. Well, so why does this mean that there are infinitely many solutions rather than no solutions? So if you think about it, x and y could be anything, and still we'd have 0 equals 0. So that's why this, like, sort of, tautologically true, this equation, which doesn't really give you any information, that's always true no matter what x and y could be, that means that we end up with infinitely many solutions. All right, now let's do 24. So here's the problem written out, and then here is Nicholas's solution, which we'll watch now.
So I'll be going over number 24 out of section 5.2 for elimination methods for operators. Here it's already in operator form. So for the 2x2 systems, I use this equation. And then for the polynomials, I set L 1 through 4 based off the equation. So here you can see L1, D, L2, D plus 1, L3, D squared, D2, and then L4, D2 plus D. So if it turns out that L1, L4 minus L2 and L3 is a 0 operator, the system is degenerate, which is shown here. So showing how it factors out, which D3 plus D2 minus D3 minus D2 we set equal to 0, which means the whole operating system is degenerate.
So Nicholas did this a little bit differently, which is fine, which is good for being able to demonstrate to you. So he did this kind of like the general way. So imagine that we have, sort of whatever operator there. So he referred to these as L1 some operator x plus L2 y equals F1, and then L3 x plus L4 y equals F2. Then you can, like, the general way to eliminate this, which is more or less exactly what L did as well, but we can do L1, L4 minus L2, L3 of x equals, and then we can do, so if we eliminate y, then we would end up with L4 on F1 minus L2 of F2. So something on the right-hand side, whatever you get when you do the same thing on the right-hand side. So that's basically what L did before, E-L-L-E, not the operator, L. But what Nicholas has done is first looked at what's this thing. And so he found that in problem 24, if this equals 0, then what you end up with is you get a degenerate system. So the one thing that that he didn't figure out, that he didn't answer, is whether there are no solutions or infinitely many solutions. So let's think about what we would have if we did this out on the right-hand side. So for our problem, L4 F1 minus L2 F2 would equal, so L4 is this one, that's L4, So we have d squared plus d operated on f1, which is what's the right-hand side in the top, so e to the t, minus L2, and that's this one. We're working with those because we eliminated y. So d plus 1 operated on f2, which is 0. So that equals d2 on e to the t is just e to the t plus e to the t minus 0 equals 2e to the t. So what our system, this says that our system is equivalent to, well, on the left-hand side we have 0 because that operator is 0. And on the right-hand side we have 2e to the t. Well, so obviously that never is the case. So no choices of x and y make that true. So that means there are no solutions. So if L had gone and done this the same way, then working out that expression would have given 0 on the right-hand side. So she got 0 equals 0, and that means infinitely many solutions. And in this case, we have 0 equals something that's non-zero, and that means that there are no solutions. And so that's the difference between these two problems. So thanks to Elle and Nicholas for your solutions, and that's it.